All right, in this lecture, we want to look at a couple of examples of parametric functions and their parametrized curves. So this first example is a fairly simple, straightforward example. In this example, we have two equations for a parametric curve. So we have x equals t and y equals t squared. And we want to try to figure out what this curve looks like in the Cartesian plane that we're used to. So let's draw some axes here. And we'll try to figure out what this curve looks like. So here's our xy coordinate system. Now to try to figure this out, what we can notice for this curve, for this equation especially, we've got this nice equation that just x equals t. All right. Not only that, but x equals just plain t, and y is in terms of t on the other side, right? And so if we put these together, we can say, all right, well, x equals t, y equals t squared. Why not just plug in this into this t, right? And so this tells us then, of course, y equals x squared. All right, and so not only this, so we've got this equation here, y equals x squared. We know what that graph looks like. But not only that, but in this equation right here, there are no restrictions on the values of t or x. So x is just equal to t. And so what we get from this, in terms of the parametric curve that corresponds to this function, is we get the entire parabola, y equals x squared. All right, so this is the graph of that parametric function. We get the whole thing, but we don't just get this. So the way I've drawn this parabola, I've drawn the arrows both going up. This is usually the way that we draw it, just to indicate what the curve is doing when it goes off the screen, right? But actually, when you parametrize a curve, you get more information than just what the shape of the graph looks like. In particular, what you have now is that as t increases, so one way to write this is as t increases, as t is getting bigger, x is getting bigger. And I think I said in the last video that physicists like to think about the parameter t as representing time, and then the curve of this, the curve that this traces out is like the path that a particle will take as time goes on. So as t is increasing, x is increasing. So that tells us that as t is increasing, our particle is going out the curve this way. And so we don't just get the parabola, we get an orientation to this curve as well. Our particle, our little particle, is traversing this parabola from left to right as t increases. And that's called the orientation. The orientation of this curve. In this case, it's a parabola, right? But of this parametric curve. So that's extra information that we didn't get from just writing this equation y equals x squared. If you just write y equals x squared, you have no idea which way a point is moving along the curve. You just know that the curve exists. Okay? So let's look at a couple more examples that are very similar, but actually a little bit different. So this one, again, we've got two formulas here, one for x, one for y. The first one, x equals e to the t, and the second one is y equals e to the 2t. But by our exponent rules, we know that e to the 2t, so when you have a product of exponents, you can factor them out, and we could write this as e to the t quantity squared. And once we see this, now based on the last example we just did, oh man, we've got a good idea. We're just going to plug that into, we're going to plug x in for e to the t, because that's what it equals, right? That's what we're told that it equals. When we do that, we end up with, look, the same exact equation, y equals x squared. And so, okay, this must be a parabola, right? So we start to get ready to sketch this thing. We draw our axes. We're ready to draw the whole thing, right? But it turns out for this one we need to be a little bit more careful, because this formula for x is more restrictive than the last one. So this says that x equals e to the t. Sure, t can still be anything. There's no restrictions on t. The domain of e to the t is all real numbers. So t can be any real number, but no matter what, for whatever real number we plug in for t, x is not going to be any real number anymore. So when we do this, we end up with that x has to only be positive. Okay? And in particular, when t is equal to 0, x starts at 1, right? T equal to 0 corresponds to x equal to 1. All right? So our initial point on this curve, if we think of 0 as like time equals 0, is happening when x is equal to 1, and the same thing happens for y then, right? Because if x is 1, y is 1. So we know, we've already plugged in that y is equal to x squared, so we really just have to figure out what's happening to the x, and then we can plot the curve from there. All right, the other thing is we've got this restriction down here that x must be positive, right? So as t approaches negative infinity, our x is going to approach 0 from the right. And so this side of the curve, we're never going to get to the origin, but we only get this portion of the parabola over here. That green part corresponds to t negative, and the orientation is that, is that as t goes to negative infinity, we approach this point. So as t increases, our particle is moving away from the origin. All right, we always draw the arrows on the curve in the direction that t is increasing. This right here is decreasing, right? That's decreasing. All right, on the other hand, as t approaches positive infinity, what's going to happen to x? Well, x is going to get really big really fast now, right? So x also approaches infinity, and this is going to fill out the other side of our parabola. I don't have a scale here. That looks a little tight, but the idea is that x is heading out real fast out this parabola, right? So this orange portion corresponds to t greater than 0, and again, increasing is heading out the parabola away from the origin. Okay, so we've got two different parametrizations of the parabola, but they lead to two different curves, actually. It's not the entire parabola on the second one. In fact, it's only the right-hand side, and it does not include the origin. So we don't have that point at the origin. All right, I've got one more example, and now we're starting to see what's going on here. Very, very similar again, right? This time, x is equal to sine of t. Y is equal to sine squared t, but as we know, sine squared is just a lazy way to write sine of t quantity squared. Okay, and so once again, we see, all right, there's x. We plug this into here. We get, once again, the parabola. But based on what happened with the last parametrization, we're worried that Justin's trying to trick us here, and so we're ready. We're gonna think more carefully about this one, right? So we know at least that the graph of this thing is going to at least be a portion of the parabola, but we're prepared for the case where it maybe is not the entire parabola. So if we think back to what we did on the last one, we've got this equation for y in terms of x. So if we can figure out what's happening to x, then we can certainly sketch the graph and plot what's happening with y, because we know that this is going to be a parabola. So let's think about this. When t is equal to 0, so time equals 0, that's like your starting point. What happens to x? Well, x is equal to sine of 0, and that's 0. So this one does start at the origin. In particular, it passes through the origin. The last one didn't, right? And as time increases, so I'll just draw it this way. As time increases, what's going to happen? Well, x is going to go out the sine curve, right? So as t increases at first until it gets to what? Pi over 2. The x value is going to increase until it goes out to 1. Sine of pi over 2 is 1. And so this is going to trace out this much of our parabola. All right, and this, again, comes with an orientation. And so our particle is moving this way. All right, but what happens when, so this point right here corresponds, right, to t equal pi over 2. What happens to the sine function as t goes past pi over 2? Well, it starts to decrease again, right? So this point is then going to turn around and trace back over everything that we just covered, right? It's going to go back down to the origin until it gets, okay, so this was t equal to 0. We get back t equals pi. It comes back to the same point at the origin. And then it's going to continue to become negative. So from pi to 3 pi over 2, this becomes negative. So this point over here is 3 pi over 2. And now we can see what's going to happen. It's going to then turn back around, and this curve is going to, this particle is just going to keep going bing, 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 back and forth along this portion of the parabola, and it's never going to leave this range in the x direction that's bounded between x equals -1 and x equals 1. All right? So this orientation is very complicated because it keeps retracing over the same curve over and over and over again. All right, so there's 3 examples. They all kind of correspond to the same curve, but really they do not. They do not, okay? As parametric functions, they're very different. So make sure you understand the differences between each of those.